Hello, welcome back to part 2 of our look at heart anatomy, where during this session we are going to focus our attention to electrical stimulation within the heart. So we know that we have these intercalated discs, we know we have gap junctions, we know we have these desmosomes, we know that regulation of the ventricles and the atria, that we have this ability to stimulate all of the cells that are associated with the ventricles to contract at the same time. What does that look like, though? How does that happen? And so that is what this video is going to be focused on. And so with that, let's jump in and take a look. So first of all, remember that we have these intercalated discs, all right? And within these intercalated discs, specifically within the gap junctions, so this is where we're really targeting our focus here, is within these gap junctions. The gap junctions become leaky to ions. And specifically, the ion that we are most interested in is the ion that regulates and controls action potentials, which is, everybody should be screaming it at your computer screen right now, sodium ions. We know that the sodium ion is the great initiator of action potentials. And so it should be no surprise that the ion that we are most interested in seeing move across the gap junctions to stimulate electrical conductivity is the sodium ion. And because of this coordinated effort to allow all of these gap junctions to become leaky at the same time to sodium ions to stimulate contraction among all of the myocardial cells located within both of the ventricles and both of the atria at the same time, we have the ability to have coordinated contraction. And this ability is what we define as autorhythmicity. This ability to stimulate a coordinated contractional event. And again, it's the gap junctions that are facilitating this by becoming leaky to sodium ions. And remember that these gap junctions are vertical articulation between the cardiocytes, and it's happening at the location of the intercalated discs. And so, as I've already kind of alluded to, if we take a look up here, our cardiocytes become permeable to sodium. And the reason why they become permeable to sodium is due to the gap junctions becoming leaky. Now, remember, gap junctions regulate permeability across the cell membrane. And so when those gap junctions are quote-unquote tight, you have less permeability. You have more cell activity. But as the gap junctions open up, as they loosen up, as they become less restrictive, you have more permeability. Now, the question that we need to look at is, how do these gap junctions become permeable to sodium? And to understand that, we have to back all the way up to the right atria. And it is the upper portion of the right atria that we need to focus our attention to in order to begin to understand how cardiocytes all the way down in the ventricles and the gap junctions lining those intercalated discs become leaky and permeable to sodium to generate an action potential that simultaneously leads to contraction across the ventricles. And so we begin our look in the right atria with a structure that is defined as being the sinoatrial node, the SA node. And it is within the SA node where we begin to see this coordination of gap junctions becoming leaky. And again, coordination is a key factor to this whole process. So let's go ahead and let's jump into this. Let's take a look at this. All right. First of all, we have sodium channels found within the sinoatrial node. All right. And so so kind of picture this flow here, if you would. You have, let's say, adrenaline that is secreted, released through the phrenic nerve. Jot this down. So the phrenic nerve we know is a branch off of the brachial plexus. And the phrenic nerve has the ability to innervate the heart, the diaphragm, and it goes down into the GI tract as well. The phrenic nerve takes a very similar route as cranial nerve 10, the vagus nerve, does. They have opposing functions, but they take the very similar path. So the phrenic nerve is where we see things like adrenaline be secreted. And so adrenaline is released into the right atria, innervates with the right atria, one branch of it does, where adrenaline is released, and that stimulates the SA node to become permeable to sodium. And when that happens, an action potential is generated, a series of action potentials is generated and released from within the SA node, and that stimulation spreads throughout the right atria and even into the left atria. And so if I draw a heart, please do not mock, do not laugh at my attempt to be an artiste. There's the right atria. Here's the left atria. There's the left ventricle. There's the right ventricle. Right atria. Right ventricle. Left atria. Left ventricle. And it's within, again, the right atria where we've got this structure that is defined as being the SA node. And when stimulated, the SA node will send action potentials out to the left atria as well as throughout the right atria. Now the purpose behind this is to stimulate atrial contraction. And we're going to talk more about this in the next video, but atrial contraction is what's going to lead to blood moving from the atria down to the ventricles, again in a coordinated motion. But the other thing that happens here is right about here in the atria, there's another node, and that node is what we call the AV node, the atrioventricular node. And the atrioventricular node, the AV node, kind of is the intermediary between the first part and the third part of this process, which we're going to get into. But the other thing is, the nice thing is, the AV node can act as a backup to the SA node. It fires slower, and we're going to talk more about the firing speed of the action potentials and how often they send signals here in a little bit. But the AV or the SA node is very quick, very rapid. But when it sends that signal to the AV node kind of holds it for a couple seconds before it passes it on. And so its rate of action potential generation is slower than that of the SA node. So let's back up here one more time. The SA node is stimulated through the phrenic nerve and adrenaline to go ahead and become leaky to sodium, which is going to generate action potentials, and it sends those action potentials, it sends the electrical stimulation to the left atria, throughout the right atria, and it's going to stimulate contraction within the atria to send blood down into the ventricles. But at the same time, it's going to send an electrical stimulus to the AV node, and that AV node is going to hold on to that for a couple seconds. It's a little slower to respond than what the AV node is. By the way, the SA node is what we define as the pacemaker, because it really does regulate the rate at which the atria and the ventricles contract. But when you hear of somebody getting a pacemaker, it's because the SA node is not functioning the way that it should, and very often the AV node malfunctions as well, and so an individual will have a pacemaker put in. The pacemaker is actually regulating the AV node, and so the artificial pacemaker is taking over the role of the SA node, as an aside. So the atrioventricular node, so named because it is between the atria and the ventricles. It's found in the lower right-hand portion of the right atria. All right. And so the AV node receives this stimulation, receives this impulse, and it passes it off to what we define as being the atrioventricular bundle, or what you will also sometimes hear it referred to as the bundle of His. And the bundle of His is located right about here. And so now this action potential is going there. All right. And again, this is the bundle of His, or also referred to as the atrioventricular bundle. And from there, the atrioventricular bundle splits into a right and a left branch. And as you would assume, the right branch comes down to the apex, comes up the myocardium, and splinters off. And the left branch comes down to the apex, comes up around the left ventricle, and it also branches off. Right? And so this here now is the right and left branches of the bundle of His. Now, why is that important for us to understand? Well, because these branches that are coming off of the right and left branches of the bundle of His contains modified or specialized cardiocytes that don't act as traditional muscle cells. In other words, they don't engage in contraction. Instead, what they do is they engage in electricity or electrical stimulation. And we refer to those little fibers, I'm going to change colors here one more time. We refer to those fibers as Purkinje fibers. Purkinje fibers. And I think you can see that a little bit better now. This is an E, not an I. Sorry about that. There you go. And these Purkinje fibers are specialized myocardial sites that don't engage in contraction, but instead gauge in electrical stimulation. Okay. And so what does that all look like? Again, here's the formal notes for Purkinje fibers. So what does that all look like? Well, this is what it kind of all looks like. All right, here again we have the SA node. It's sending out the signal once it's stimulated, due to usually adrenaline. It's going to be stimulated here. Right? It's going to stimulate contraction within the left atria, within the right atria. Right? But right here is the AV node. Again, the lower portion of the right atria, kind of between the atria and the ventricle. It's going to be stimulated. Remember, it fires at a slower rate than what the SA node does, but it's going to pass that off to the bundle of His, which is located right about here. The bundle of His is then going to separate into the right and left branches of the bundle of His. And then you're going to come to these Purkinje fibers. And again, the role of the Purkinje fibers is to stimulate these specialized cardiocytes that are going to engage in electrical conductivity rather than contraction. But that electrical conductivity is what's going to diffuse through those myocardial sites to go ahead and cause the gap junctions to open so that they become leaky to sodium, so we can engage in contraction in all of the cells all at the same time between both the right and the left ventricles. This concept of that we refer to as autorhythmicity. And this slide, you actually have this slide. This slide is a nice overview of what we just went over as far as the conduction within the heart. And so you can go ahead and click on this link up here, and it'll actually take you to a video or a series of videos that you can then go ahead and watch and kind of review this process. I'm not going to do that here for obvious reasons, but that is definitely something you can do and review on your own. And just to kind of set you up for the next video, here is some terminology that you need to know prior to going and starting video 3, which is on the cardiac cycle. And so we're going to look at how does all of this that we've been talking about start fitting together and piece together. How does the anatomy lead to an understanding of the electrical conduction, and how does that lead to an understanding of movement of blood and changes in pressure throughout the heart? Because all three of them are going to start fitting together. This is like one very odd, weird menage a trois or threesome between the anatomy, the electrical conduction, and fluid mechanics. Pressure, changes in pressure throughout the heart. So atrial pressure is just that. It's the pressure within the atrium. Ventricular pressure, this isn't rocket science. That's the pressure within the ventricles. Arterial pressure is the pressure that's found within the aorta and the pulmonary trunk. Do understand, though, the difference between systole and diastole. Systole is high pressure phase that often or that will lead to contraction. Right? So when a chamber is experiencing systole or high pressure, that is when it will go ahead and engage in contraction. But when a chamber is in dystole or low pressure, then that chamber is dealing with relaxation. So both the right and left ventricles experience systole at the same time. They both experience diastole at the same time. Same thing with the ventricles. Both ventricles, the right and left ventricle, will go ahead and experience systole or high pressure that leads to contraction at the same time. And diastole will also lead to relaxation or low pressure in both the atria at the same time. And then there's a split second between contraction and relaxation where there is no change in volume. In other words, blood is not moving anywheres, either into the atria, out of the atria, into the ventricles, or out of the ventricles. Everything is static, and that's what we define as being isovolumetric. In other words, there is no change in the volume of blood that is moving through the heart. And so with that, for you to kind of review and look at, I will go ahead and stop here as we now prepare to go ahead and look at the cardiac cycle in video 3. And so keep reviewing, keep answering those questions, keep asking those questions, and I'll catch you on the flip side.